Okay. I don't freak. Six, 8, 9, 0. Okay. 4 minutes today. It's getting better. Not as bad as the 15 minutes that happened twice. All right, we're ready to go. This picture looks familiar to everybody? Yeah, I've tried to draw that picture several times. I've succeeded a couple times, maybe, in drawing that picture. All right, so we're gonna, and so actually this corner up here is sort of the zoomed out view of what this picture truly represents. So the picture represents what we call orthogonal cutting, and it's really like, has anybody any carpenters in the room? Nobody does carpentry? Never hung a door? No? I'm the only one in the room that's ever hung a door. Really? You've hung a door. All right. So do they always fit the door jamb opening? Depends how good you are, right? But one of the things we often do when they don't fit the door jamb opening, it's usually easier to change the door than it is to change the house, especially if it's an old house, and sometimes those door jamb openings do this in old houses. So what you do is you take a wood plane, and it's got like a sharp cutting edge on it, and it's got a handle that allows you to push that sharp cutting edge, and you push that across the top of the wood, and it skives off a little, it's basically a chip off the wood, right? So that's orthogonal cutting. We're doing the same operation here, and it's almost exactly the same as doing a regular turning operation in a lathe. The difference is here, our tool is much wider than the chip, right? And so what that means is the forces and everything that's going on are constant all the way across where that chip is being created. Now in this scenario where we're cutting with the tool's got an end, right? This is the tip of the tool that makes these grooves that go across here. The tool's got that end in it, and so things are going to change. The physics is going to change as you get to the tip of the tool, right? Because the side, as we go around the radius, I'm not going to bother to try to do this thing, but as we go around that radius that's at the edge of the tool there, as we do that, that side edge cutting angle is changing, especially if it truly is a radius, right? It goes from whatever it is to 90 degrees, right? That side, it goes from whatever it is to 0. It's even worse, right? Because if it was 90 degrees, then it affects the feed just a little bit, the uncut chip thickness, right? So when we do our modeling, right, as scientists, we want to do modeling to understand how these processes work. When we do our modeling, we like to simplify it. And so what we do is we assume that we're doing orthogonal cutting, even though we know that at the tip of the tool we're not. If you were turning the face of a tube, you could do true orthogonal cutting in a lathe, right? So if this was hollow in the center, and I came in with the tool along the face as I turned the part around, then I could be doing orthogonal cutting in a lathe. But anyway, it doesn't matter. This orthogonal cutting, and here's our representation. So we ended yesterday looking at this resultant force, right? The P that was our resultant force. It doesn't show up on my mouse doesn't show up on the thing. Huh, that's lame. So when I wiggle the thing around and try to point at stuff on the screen, you guys don't see that, huh? We're 3.5 weeks in and I just noticed that. Sorry, that's my bad. Anyway, maybe there's a highlight thing. The P, the vector P, that's the resultant force. That's what is creating the chip. What we're going to want to do, I think I am going to switch back and forth then. All right, so I got my tool, got my chip, got my workpiece, and so chip, workpiece, tool, right? And P is our resultant force. So we know that there's going to be a friction force that's lined up along this plane. And we know that that friction force plus the normal force has to equal P, right? Because we know from our knowledge of friction that friction force plus normal force equals P. When we ended yesterday, we were talking about this velocity being in this direction of the workpiece past the tool, right? It's the opposite direction if you're looking at the velocity of the tool past the workpiece. But the relative motion of the tool and the workpiece has this velocity, and we said that that velocity equals what? It equals the surface speed right? So that velocity is the surface speed, and it comes from the rotation of the spindle. So as we rotate the spindle, that surface speed is generated, and so we know that it is pi times the diameter of the rotating thing, whether it's the tool or the workpiece, right? That's pi times diameter equals distance over revolution. And if we multiply by revolutions over minutes, we can get distance over minutes. And then we remember that when we talk about surface speed, we typically talk about feet. And when we talk about diameters, we typically talk about inches. So we got to do that 12. We got to do the conversion from feet to inches. And if you Google this, actually, let's do that. Google surface speed in turning equation. That sounds like a fair Google, right? What's the equation for surface speed and turning? Has anybody ever Googled an equation when they wanted to know what it was? Has anybody never Googled an equation? Okay, so it's a fair thing. We do this all the time. Surface, in fact, I've asked Siri before, but Siri's kind of dumb. She's not an engineer, not at all. Is Alexa more engineering like? Alexa any better? Yeah, I don't know. We had an Alexa, but my daughter just took it to her room and sings and dances with it. I don't know what she does. All right. It says here, can you guys see that? Should I zoom in? Whoa, that's a lot of zooms. RPM, right? We were finding what's SFM, but you could reverse the equation to find RPM, right? We all know how to move the sides of the equation around. RPM equals SFM divided by diameter times 3.82. That 3.82 is often 4 when you find an equation for this. So why is it 4 or 3.82? Yeah. 12 divided by pi. And so if you're at the machine tool and you're trying to think of this quickly in your head, this often would come up in manual machining, and you're putting a new tool in and you got to turn the levers on your machine tool to make it spin the right speed. And so the machinist would be doing these calculations in their head, and it's way easier to use a factor like 4, or it's even, you're dividing by 4. That makes it even easier, right? Because it's just a quarter. It's 25% of whatever the number would have been. It's really easy to do that math in your head. So very often you'll see people, and this is where I talk about if you memorize the equations, you guys feel free to memorize equations. But if you memorize equations and you don't always know where they came from, then if something goes wrong, you won't understand what that 4 was, right? So anyway, so RPM equals SFM divided by diameter times 4, or actually the 4's on the top of this equation, right? Because there's no parentheses. Anyways, feel free to Google equations. Think about what makes them true, though. Don't just accept the equation that you read. Okay, but anyway, that's our velocity. That's our surface speed. Switch back to the other view. So that's our surface speed. Is that velocity going by there? It happens because the tool or the workpiece is rotating in the lathe. That happens because the tool is rotating in the mill. So when we say power equals force times velocity, we mean this velocity. So what force do we mean? If we're going to multiply the two things, because they're vectors, right? You can't just willy-nilly multiply them, right? So we need a force that's lined up with that velocity. So what if we drew a force here? Now we'd have to have another, I guess that was too far. Right, the tip of that arrow should probably be right about here. We have to know that there's a force that adds to it to get P, because P is the total force in the system. That resultant force is the total force in the system. So if we have this one plus this one lines up with our surface speed. And that's cool because we can read the power of the spindle, right? And we can estimate the efficiency of the machine tool after we read the power of the spindle, and we can then know what that force is. We call that FC. That's FC for the force of cutting. And then this one that we have to add to it. And so this one that we're adding to it is what keeps the tool from flying away from the workpiece, right? The workpiece is trying to push the tool away. We've got to have this thrust force, FT. We had FC and FT. Yesterday we talked about the friction and the normal force, F and N, because that's what we always use for friction and normal, right? So we can see in this FC, we know is force times velocity. Or so is power divided by velocity, right? Is FC. So that's pretty cool. So we know that. Switch back to the slides, I think. All right, so we got our FC and our FT, and you can draw them in any way that you want to do there. But this is pretty cool because we can also relate those. If it's the here's our friction, and go. There we go. There's our friction force and our first normal to the friction force. And there's also what we haven't talked about. There we go. Is the fact that there's a force system. So the thing that actually makes the chip form is the shearing of the material, right? We're actually breaking the material in here. And so remember we had our KP value if we're estimating power for cutting. It has all to do with the material properties. And so there's that force in that shear plane that lines up there, and then you got to have an orthogonal force, so we call that one the force normal to the shear plane because we're engineers, we're not poets, we're not very imaginative. And so those are the three different force systems that you're going to encounter when you're analyzing, modeling these kind of operations. Here's all three of them drawn in one thing. You can actually make like a circle and all the tips end up on the edge of the circle. I didn't bother to do that. All right, so, and that shear angle is going to be a big factor in how much that shear force is. So that shear angle, as it changes, the shear force is going to go up and down. And the rake angle again, so the shear angle happens because of the material and the rake angle. And that rake angle we get to set, we get to select that. And so this guy named Gene Merchant, he realized, he did a bunch of these experiments. He came up with this formula, this model here, whereas the shear angle is 45 degrees minus the friction angle over 2 plus the rake angle over 2. He came up with this relationship after doing a whole bunch of experiments. And that allows us, if we know so also, come on. Okay. RT is the ratio of T1 to T2. So those are our uncut chip thickness and our chip thickness. You can't see the T2 at the bottom of the slide there, but RT is the ratio of T1 to T2. And the tangent of the shear angle by geometry has to equal RT cosine of the rake angle divided by, let me write the equation because it's not coming through on the slide. So we're looking at it. So we've got our tool. We've got our chip. We've got our workpiece. So this here is the T1. This here is T2. RT equals T1 over T2. And this is alpha. So that's our shear angle. Oh, sorry, that's our rake angle. There is our shear angle. Okay. And so tangent T1 over, sorry, tangent You notice how I'm not doing this from memory? All right, so tangent of the shear angle is RT times cosine alpha divided by 1 minus RT sine alpha. So you can, the shear angle and the rake angle are related by that relationship for every material. And the rake angle, and so this tau is the friction angle. That's the angle between the normal force and the friction force, are related to the shear. So you can transfer from one coordinate system to the other one that way. All right. You also, if you know the cutting force and the thrust force, you can figure out the friction and the normal force. And so again, it's related by the rake angle, and that makes sense because that friction force is aligned with the rake face, right? And so you can use these equations to make those changes. That friction coefficient, remember we talked about the fact that we don't know what the friction coefficient is? How do you figure out friction coefficient? If you were to do an experiment to find out a friction coefficient, what would you do? You could walk on the sidewalk today, right? Friction coefficient's variable on the sidewalk today. Did anybody walk to school today? Does anybody have wet feet right now? I do. Pretty sure that water will run out of this one if I tip it upside down. Right? Okay, so that friction, so if you wanted to know, here's a table nobody's using. Perfect. If I wanted to know the friction between my pen and the surface of the table, what could I do as an experiment? I could push it, right? Then I would have to somehow measure the normal force and somehow measure the pushing force, right? What could I do that's even simpler? Well, first off, what's the normal force? Yeah, it's the weight, right? It's the force of gravity acting on the mass of the pen, right? And so we could know that. It's pretty easy to find out the mass of the pen. Just get a scale and weigh it. Now, what's the normal force? It's either sine or cosine. I never remember which one, right? I always look those things up, right? And eventually, we get to an angle where the pen slides, maybe. It's got good friction. Somebody's going to have to tell me when it slides. All right. Anyway, you guys get the idea. We wouldn't do it too much with the rotating wheels. All right, so you could do an experiment really simply if you know the mass of the thing. You put it on the other surface, you incline the other surface until it starts to slide. Then you know at what normal force it started to slide. When did it overcome the friction? You can't do that so much with the chip forming on the edge of the tool. Because when you're talking about the chip forming on the edge of the tool, you can't really observe the angles that closely, and you don't, because you're pushing it, right? You need to be able to measure those forces. And it turns out you can't just say, well, let me take some of the workpiece material, and then we take some of the tool material and put it on a table and then tip the table up, right? Because it's going to depend on the temperature also. As the temperatures get really hot, the friction coefficient is going to change. For us here, it's fine, but sometimes the cutting temperature exceeds the melting point of the material. When that happens, you actually stop cutting and you start welding, which is bad. because then it makes like the chips stick to the tools and all that stuff. But those cutting temperatures, the temperature that's at that tool chip interface can be close to the melting point of the material, and that will impact that friction coefficient. But from the geometry of the system, we can actually calculate the friction coefficient if we know these things. So it's nice that the friction coefficient is actually just the tangent of the friction angle, or the friction force over the normal force. So that's kind of cool. All right. There is, and I'll put a link to this. I think there may already be a link to it in the syllabus. I don't need Alt Tab. I just need to switch tabs. Syllabus. Close. If we go back in the syllabus to the slide labeled resources, no, there is no link to it here, so I will add the link to it. But I have compiled a collection of all of the equations that we might use in ME1800 for you. So you could, as I spout the equation and try to write it on my whiteboard, you could try to copy it down, or you could use the list of equations that I have provided. As we get the next couple weeks of the class, we're going to do some more mathy stuff in the class. And so all that stuff is in there. So I'll put a link to it here in the syllabus under the resources tab so that you can have access to those things. Because a lot of this is, and a lot of this engineering work that you're going to be doing here in general as engineers is about understanding the physical processes, knowing that something is possible, and then figuring out what equation predicts that. Does that make sense to you guys? And so if you want to do the sciencey part of this, you could be figuring out what those equations are, and you could be extending the knowledge of the humankind. And if you want to do the engineering part of this, you could be looking at reference books or Googling what's the equation for. Does that make sense to everybody? Okay, that's great. So what I've got here is a list of equations that are important to the topics we talk about in ME1800. That link is in here. It's got all the stuff that were on these slides and the slides that I didn't use for the last 2 days. And it'll allow you, if you know what the cutting force is and you know what the thrust force is, you can figure out what that shear angle is. You can figure out what the other things are. And a lot of this is by geometry and vector math. I don't expect you to memorize it all. I don't expect you to even necessarily be able to, I expect you to be able to derive any of the equations from first principles. I won't expect you to demonstrate that you're able. Is that fair? I think any one of us, if you got into WPI, if you're sitting in this room or watching live on TV, you have the mental capacity to have derived all these equations. But when I was in grad school, one of the things that my advisor first told me was something that he said he learned in grad school. And he said that a few years in the lab could save you a few days in the library. Come on, somebody's gonna laugh at my jokes. At least without pre-mask, like BM, right? We have BC and AD and all this. BM, before masks, I can at least see if people were grinning when I make a stupid joke. It's even worse now, because what used to take a few days in the library, you can do in a few seconds on Google, right? And you can even get the journal papers on Google, because you just go to Google Scholar, right? So anyways, so you could get to the edge of knowledge and be a scientist and go figure out more knowledge. And there is active research in the world right now in machining. We've been doing machining for a long time, right? When did we start doing machining as like an industry? Anybody know? Yeah? So it got a big bump in the late 1800s when we got steam engines. Right? So as we started getting steam engines and we could build factories and stuff, we got a big bump then. But like doing machining as an industry pretty much started as soon as we had a community. So I don't know, a couple million years ago, billion years ago, how long have people been making stuff, right? Stone tools. So you pick up a piece of flint and you hit it with another rock. The physical process there is the same or similar process to the things that we're doing now. So we've been doing machining for a long time, for as long as we've been using tools. But people are still doing cutting edge research in machining. Right now, the hot topics are, how small of a chip could you make? So what's the thinnest T2 that you could possibly create? There is a minimum. There's a threshold there. What's the minimum cutting force that you could possibly have? So people are doing that kind of research and figuring those things out. The other thing is, and we're going to get to this next week, is mostly focused on this topic, if I remember the schedule right, is how fast can you go from stock material to finished part? That's pretty important economically, right? How quickly can you do it? And so doing it faster is not necessarily more efficient, but if you can sell the parts faster than you can make them, and then you should make them faster, right? So as long as you can sell the parts faster than you can make them, you should make them faster. Okay, so I'm gonna, and the reason I did this little segue here is because we changed topics at this point in the lecture. It's still talking about machining, but we're not looking at the forces at the tool chip interface anymore. Now we've stepped back and we're looking now at what's happening to the stock material, what's happening to the machine tool. So if you're turning a part in a lathe, so let's say that we're turning a part in a lathe and we've got our cutting tool acting on it. If we know the power, right, because we can measure the power, if we know the power, then we can easily know what that cutting force is. And that cutting force is acting in this direction. So the tool is pushing up on the workpiece right here, right? So what happens when I push on something? First, what do we call it when we push on something? So if I do this, I'm applying a force to the table, right? But the force is applied over an area, the area of my hand. So what's force over area? It's pressure, right? And so when I apply a force or a pressure, so the same thing's happening at the tool chip interface. We're applying a pressure, force over area, on the workpiece as a whole. So we're not really concerned about what's happening at that tool chip interface. Either it's making a chip or it's not, right? If it's not making a chip, then something's breaking. But if we're in that steady state, if we're in the point where we're making a chip, we're applying a pressure here, right? And so what happens to every material when you apply a pressure to it? Come on. Oh. Turns out that control caps lock doesn't change anything. Control tab does, or alt tab, or whatever it is, command tab here on the Mac. So what happens to anything that we push on? So yeah, go ahead. Right. Well, it pushes back on us unless it's accelerating. But so we're actually, what we're segueing into now is talking about stress. And so there's an entire class here at WPI that you could take that's, I think it's titled Stress and Strain. And so I guess that means for 3.5 weeks, you talk about stress. And for 3.5 weeks, you talk about strain because it's stress and strain. I actually think for like 7 weeks, they mix them up. You know, it's funny. When I was a student here at WPI, I never took that class, which is really weird because it's almost impossible to graduate with a mechanical engineering degree here without having taken that class. But I'm certain I didn't take that class. Now I have to teach it. So what is stress, though? Yep. Yeah, so stress is actually the same as pressure, right? It's force over area. It's the force applied over an area. So in engineering talk, sometimes we call it pressure, sometimes we call it stress, but it's got the same units. And so it's force over area. In this case, if we're pushing and pulling on a cylinder, then it's force over pi r squared, right? So it's easy to know what the stress is. Now, I guess we've all talked a lot about stress, stress lately on campus here, right? Think about, because we talk about engineering stress or we talk about mental stress, right? Well, let's just take a step back and think about mental stress. What is mental stress as compared to engineering stress? What makes us feel stress as people? I know we all feel stress. A lot of us have been stressed out a lot lately. What makes us feel stress as people? Yeah. So like work, like schoolwork. So needing to do work. And it does sort of have that time factor in there, right? I actually so if we draw a set of axes here, and we put time on this one. So we get time on the bottom axis. And on this one, let's put motivation. And so I'm talking about class projects, MQPs, deciding that you want to lose weight, all these things, right? So you can't have a goal. So you can't have a goal without setting some time limit. So if I say, here's my time axis, here's my motivation level to do the thing. It really doesn't matter what the thing is. It could be my homework tonight, right? If I'm talking about tonight's homework, I've got a shorter time scale because by tomorrow, tonight's homework doesn't matter anymore, right? So the best thing about deadlines is once they've passed, they don't matter anymore. Oh, and once it's time to do something, you're ready to start, whether you thought you were ready or not. That's another thing that comes up. But so if we have a lot of time, so out here when time is a big number, we don't have very much motivation, do we? Typically, for most projects, when there's a lot of time, I feel like, well, I could get to that later. And so as I start getting less and less time, maybe the motivation goes up a little bit, goes up a little bit, goes up a little bit, goes up a little bit. And that now time's getting short now, right? As time gets short, motivation goes up, right? Right up in, I mean, let's say that's the drop dead date, the deadline. It could fall right off after that, right? If it doesn't matter anymore. There's sometimes where, so sitting at a red light, driving your car, and you're texting on your phone, and it turns green, and you're texting on your phone. Because you're absorbed with your phone, you're not really motivated to go forward, right? And as soon as it turns red again, you don't have any motivation, right? So if you sat there for the whole light cycle, your motivation goes away. So there's things that make motivation go away. Let's add another axis here, though. Let's put on apparent skill level. And I say apparent skill level and not skill level Because you have an infinite apparent skill level if you have lots of time to learn how to do the thing, right? If you still have time to learn how to do something, you still have that apparent skill, even if you don't already know how to do it. So learning new things. So when we have lots of time, we have lots of apparent skill. And as we run out of time, we have less time to learn the things, right? And eventually, it falls off. As we get closer and closer to the deadline, we start rushing, right? Maybe we've figured out how to do the steps by the time we get closer and closer to the deadline, but we don't have time to finish all the steps anymore. So we start going fast. It's MQP. Anybody in the class working on their MQP now? You are? So what term do you plan to finish your MQP? Next term. D term. So you were smart enough to register for D term in advance? Yeah. A lot of MQPs are scheduled to end in C term. About this point in C term, a lot of people working on their MQPs are pretty motivated, right? They're up here in the motivation graph, but their apparent skill level falls off sharply because they start staying up all night working on the project. They start trying to do things faster. And some things, physics determines how fast they happen, right? And so I would say that at this point where the apparent skill level crosses the motivation point, that's the point where motivation becomes desperation. And so if you did a bunch of work out here, though, so when your motivation was low, if you did more work out here, you can finish the project before that happens. Anyway, but at that moment where you have lots of motivation, but not very much apparent skill level, that's like the highest stress times for all of us, I think. And it doesn't matter what you're doing. At that moment when you're at this inflection point or the crossing point there, that's when our personal stress is the highest, I think. So what happens when we put a stress on either a person or a material? So what happens if I'm applying stress here to my material? Well, it could fail. If I apply enough stress, it'll fail, right? Then my hands will clap together. But really, what happens is it changes shape. Maybe with my hands pushing on this fairly rigid piece of plastic, it's probably hard for us to measure the shape change, but it changes shape. And the shape change is the result of stress. We call it strain. This was back when I was into fancy slides. And so if we measure those forces and we measure the change in shape, we can actually learn something about the material, right? We can learn that it's called the elastic modulus. We can learn that about the material. So, how do you make stress go down? So, yeah. Right. So if we want stress to go down, we can make the area go up or the force go down, right? Is that how we make stress go down? Okay. How about our personal stress? How do we make our personal stress go down? That's engineering. That's pretty easy. And we're all engineers, so we get the engineering thing. How do we make our personal stress go down? This is the same method. We could reduce the force, or we could increase the area. Just eat more, right? Right? Isn't that how we do stress reduction? The bulgy one that's photoshopped. Swear to God, I didn't actually look like that one day. But it's the same thing. And so here, if we measure the stress and the strain, we can plot the stress and the strain versus each other and get our modulus of elasticity. And so that's a material, it's a bulk material property. So the other thing, time is running out. When do we meet again? Tuesday. Do we meet on Tuesdays? Look at the schedule. I think it is Wednesday. Next week is the 8th. No lecture on Tuesday. We meet again on Wednesday. Okay, Wednesday, when we meet again, I'm going to start with this slide because I want to spend a little bit of time on it before we get into the next topic. The next topic is manufacturing economics. So we're going to be talking about the economics of manufacturing. And we're going to spend just about a day and a half on that topic. And we're going to be talking about the group project because it ties in with our group project topic. So Wednesday, Thursday, next week, we're going to be talking about the group project, talking about manufacturing economics. But I want to spend 10, 15 minutes on that next topic, which was how does the strain impact our ability to make a good part? Remember, we can't sell the parts to our customers if they aren't the things the customers wanted. So we're going to spend just a little bit of time about how stress and strain impacts our ability to make a good part. And then we'll jump into economics. All right, we're done. And end the broadcast.